So we'll now look at the assembly procedure. So the first step is an initialization step. So here we create a lookup table and populate it with the predefined symbols. And then we just go through the code. Any comments we delete, and any white spaces, because you can put blank lines and so on in your code. So we'll just make it easy to read. But when you're doing assembly, we need to delete any kind of blank spaces and remove all the comments. Then in the first pass of the code, we just go through it line by line. This is where we're not generating any code. We're basically just scanning through the code line by line. And then every time we find a label declaration, that's some kind of normal uppercase word inside brackets, we add the per label n and the line number that comes next to the lookup table. So the first pass, we're not generating code, we're just basically looking for labels and then adding the label and instruction number to the lookup table. Then on the second pass, we now go through the code line by line. All the C and A instructions with literals, we just convert them to binary instructions using the binary instruction format. And then if we see the line has got kind of a user defined symbol, so @ symbol, so it's one of these @ sum or @ total or something, we basically look in the lookup table. So in this lookup table, if we find the symbol there, we just replace it with its numeric value and then translate it to binary as normal. If it's not found, we basically need to add it to the lookup table at the next available RAM address and then translate it to binary. So the first, the first user symbol is at address 16. So the first time we come across a user-defined symbol, we'll replace that by 16. The second one will be 17. The third one will be 18, and so on. So again, we'll just look at the different instruction formats. A instruction is very easy to assemble. The first bit 15 is a 0, and then the remaining 15 bits are just a binary value of the instruction. The C instruction, it's a bit more involved, but again, it's the same simple procedure. We see a C instruction, we just replace it by its binary equivalent. Bit 15 is always a 1, and 14 and 13 are also a 1. They're not used, they're used as a 1. Get the correct A bit, so look at the table of computations, get the A bit, get the actual opcode for the operation, set the required destination, and the required jump if there is one. So this table here outlines, so these columns here show us the different computations that a hack computer can do. So there's 2 columns. The first one is for when A is 0, the second one is for when A is 1. It's just a case of finding a particular instruction. So for example, if the computation was -D, A would be 0, and then the 6 computation bits will be these 6 bits here. So this is very simple procedure. It's just finding whichever instruction, whichever computation appears in the instruction, and then just getting the value of A and the C bits. Again, the destination's completely trivial. Just look which mnemonic appears and then use it to select the required destination. So if there's no destination specified, those 3 bits are all 0. And for example, if the destination is the A register, we replace it by these 3 bits here. And it's similar for the jump. It's just a case, if there's no jump, so the jump condition's missing, we've got 3 zeros, or else, so jump greater than 0, we'll replace the 3 jump bits by 0, 0, 1.